This will be on YouTube at some time later today. All right, so we are going to stick today with constant velocity. We are doing an acceleration lab next class, and then we will get to constant acceleration. One thing to know is that the acceleration in AP Physics 1 for working problems is limited to constant acceleration. So we only have one more step up to go. You might see things that look like changing acceleration, and you have to understand them graphically and conceptually, but we don't have to do math with them, so that's good. So we only have one more layer to go on top of this. So today we're going to start with constant acceleration, and we're going to start by talking about our kinematic graphs. So those are the things we're talking about. Constant velocity on our kinematic graphs. That includes the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. Those are the traditional kinematic graphs, those three. Okay? When we talk about motion, kinematics, those are the same thing. When we talk about those, we are talking about them in terms of position, displacement, distance, right? Those are all lengths or locations. We talk about them in terms of speed and velocity. That's all how fast I'm going and in which direction. And then we're going to add today a third way to talk about them, which is how is my speed changing? How's my velocity changing? That's acceleration. So our graphs reflect that. We have three levels of graphs. We have position versus time, velocity versus time, and acceleration versus time. So far in your lab, you've only done this one, but let's talk about them. So if this is a position versus time graph, looks something like this. So instead of writing the word position, I write X, okay? X is going to cover pretty much everything we do for a while until, I keep putting my tennis ball over here. Until I take this tennis ball, drop it, throw it up. When I talk about position, even if I'm going north-south, I'm talking about the X direction because my object's on the ground. It's moving horizontally around. Whichever direction it's going, it's moving horizontally, okay? It's not going up and down. So that's why this position might say X, even if we're talking about north and south, okay? So if this is my position graph, I'm going to start with a simple one. We'll just do something like that. That's my position graph. First one up. So let's see what we know about this position graph. So I'm going to call this 1 second, call this 2 seconds, and that guy 3 seconds, so you know what I'm talking about. So my first question that I'm going to ask somebody, and again, don't have to get it right? My first question is, where is this object located at 0 seconds? Where is it located? I'm looking for a positive or negative answer. Is it located in the positive direction or in the negative direction? Yes, sorry. Positive, right? At 0 seconds, it's located in the positive direction. At what point does it have a negative position? At what time does it stop having a positive position and now turns to a negative? Yeah.
1 second.
At 1 second, right? At 1 second, it now has a negative position. Does it ever go back to having a positive position?
Yes.
No. It gets back to 0, but it doesn't have a positive position. So the first thing a position time graph can tell us about is position, right? And that's just the y component, coordinate. That's the word I'm looking for, y coordinate. Where is it? Is it above the x-axis? Is it below the x-axis, right? Since position is my y-axis on this graph, then wherever my y-coordinate is, that's my position. So at 2 seconds, maybe my position is at -4 meters, right? That would be telling me my position. Another thing this can do is tell me about displacement, right? We did this on the warm-up this morning. How far am I away from where I started? I'll give this a number because numbers are cool. I don't need to put the meters, sorry. All right. So at 1 second, at 1 second, Harshita, what is my displacement? At 1 second, what's my displacement? 2. Is it positive or negative? Have I gone to the left or right? It's actually -2 because I've moved from a +2 to a negative, or to a 0, right? So I've gone in the negative direction. If you're questioning displacement, you can always go back and use the equation for it. So displacement is equal to x position final minus position initial, okay? So displacement is how far from where I started. The object, we'll call it the object, not me, the object started, right? So at the end of this graph, I get all the way to the end of this graph. Priyanka, what is my displacement all the way out at 3 seconds? What's my current displacement? What do you think? I started at +2. This is where I am at 3 seconds. So what's my displacement at 3 seconds? 1. No. How far am I away from where I started? I started at a +2 meters. So how far away am I from where I started? I'm now at 0. 2, right? Did I go in a positive direction? Did I go positive or did I go negative to get there? Negative. So my displacement would be -2. I want everybody to see that, okay? Another thing I can look at is distance. How far have I gone? Look at this graph. In your notes, figure out what the total distance traveled was. These are the same definitions I offered before, but now you're looking at how do I see them on a graph, right? How do I notice where they are on a graph? So you're looking right now, talk to the person next to you if you need to. What is the distance traveled? Sparna, how far? 10 meters, right? That's the correct answer. How far it's moved is 10 meters. Okay, this is a position versus time graph. We're going to get more detailed into it in a second. But first we have to do a little bit of work with this kind of graph. Position time graph is the most likely graph you're going to see. It's probably the graph you're going to get. But there are 2 other graphs on this level that you could see. And 9 times out of 10, a student's not going to notice the difference between them. So let's talk about them. The other 2 are this list. I could, instead of giving you a position graph, that marker stinks. Try this one over here. Instead of giving you a position graph, I could give you a displacement graph. Ooh, I'm going to make it the same graph. Displacement and position graphs are largely the exact same thing. Okay? They're 90% the exact same thing. Yes?
So is displacement?
No, it's not. It's still in this list. So this is the main one. You could also see a DVT. And that could be either displacement or the next one we're going to talk about is distance. These are all the same kind of thing. A displacement time graph is pretty much the exact same thing as a position time graph. Literally, that's it, okay? I started 2 meters from some 0 location. My current displacement at time 0 is 2 meters. And then I traveled in a negative direction, got all the way down to a -4 meters of displacement, and then back. So displacement and position are largely the exact same thing, and you can pretty much ignore which one's which. Okay? If the question says position, you're going to do the exact same thing if the question says displacement on the graph instead. Here's the one difference. Okay? Can you tell me the actual position of the object based on the displacement graph? I can't. Okay, that's important. I can't. That's the big difference between a position and a displacement. Otherwise, they look the same. You can figure everything out the same. Okay? But a displacement time graph, right? I don't know where 0 was. I don't know. I have no idea where 0 is. I know I'm displaced currently 2 meters from 0, but I don't know where 0 was. Could have been over here. Could have been over here. I don't know. I know how far I am away from 0. Position, it's a defined system. I am 4 meters away from, or I'm 2 meters away from 0. Displacement, I might be 2 meters away from some arbitrary location. I don't know where it is. Okay, so that's the difference between these. Oh, sorry, those two. I drew them further across the board. Another key difference is the displacement, right? If we do the same thing to this graph, this is 2 meters, this is 1 second. At what second, what is my displacement? At 1 second, what is my displacement? 0. See how that's different? On a position time graph, my displacement is where I am compared to where I started, right? On a displacement time graph, now my displacement is 0. I'm 0 away from where I started. Yeah?
So for a displacement graph, when it starts at 2 meters, not talking about its actual position, we're talking about like where it was displaced from the start.
Right. At the beginning, I have this, I'm displaced from where some 0 original thing was. So the thing you have to assume with a displacement time graph is something happened first, right? Typically a displacement time graph, if we really were starting at time equals 0, I should start at 0, right? My displacement at time equals 0, I'm out where I started, so I should be at 0. So when you see a displacement time graph that's drawn differently, that means something happened first. There's time I'm not seeing, I don't know what it was, but I must have started at a displacement of 0 originally, because that's my starting point. And now I'm tracking my displacement from that starting point. But when I see this, I know this wasn't the whole story. Is that going to matter in the question? No. Let's be real. It's just not going to matter. Yeah?
If you're given with displacement is 0 in the
Yeah.
first place, then can you find it or not?
If you're given displacement, like the original displacement, yeah, you could theoretically find it. What you need is to be told the initial position, right? If you're told that your current displacement at 3 seconds is -6 and the original position was +3, now I can find where I'm currently located. I need that extra position piece. All right, last one, distance first time. Try and sketch it because it does look different. Distance is the different one. Those two largely look the same and I treat them the same. Again, most of the time you're going to get a position graph. It's not going to be that issue. But occasionally it'll say displacement. And you want to make sure you understand what the difference is between those two. Distance is just how far did I go? How far did I travel? So if I sketch the distance graph, it should just look like that, right? I can't go negative. The distance graph can't be negative. It can't be. Yeah.
So why do we add the line below the time?
Because I was sketching the graph, and so I always do. But yeah, it'll always look like that if you don't want to sketch it. It always has to be positive. My distance is always growing. Nothing changes. Okay? So, I wanted to show you that these 3 graphs exist so that you understand, yes, okay, there's a difference between position and displacement, and I might see both. There's a bigger difference between position and distance, and I need to pay attention. Okay? But the main thing we learned in our lab last class, and where we're starting today, that was kind of a review. Where we're starting today, the slope of this position time graph and a displacement time graph would be what? The slope of it is? No. We did this last class. You made a distance over time graph or a position over time graph, depending on what you chose to do, right? What was the slope of it? If you did a distance over time graph, the slope was speed. I agree. What is the slope of a position versus time graph? It could be positive or negative, Liam. Velocity. Exactly. So that's important. So the slope of these graphs, you'll very rarely see a distance one, but you could. It's important to know its speed. Okay? but this is the one you're going to see most of the time, and this is where we get velocity. So let's talk about the velocity. I have this beautiful position time graph. Blake, what is the velocity? You just have to say positive or negative from 0 seconds to 2 seconds. What would be the velocity from 0 to 2 seconds?
Negative.
Negative 6. Over 2 seconds, it would be -3, right? Because I would divide by. But I don't need the number. I don't need the number. I just want to know if it's positive or negative. So because this slope is negative, right, I have a negative velocity. What else can I tell about that velocity? Is it changing or is it the same the whole time? It's the same because the slope is the same, right? The slope is constant, so the velocity is constant. Awesome. Right? What about from 2 to 3 seconds? What kind of velocity do I have there? Positive and constant, right? Positive and constant. Okay? So, try and sketch me. We're going to introduce, now that we understand the differences between these types, try and sketch me a velocity versus time graph. Based on this one right here, we know the slope of this graph is velocity. So try and sketch me a velocity versus time graph. In your notebook, think about it. We just discussed what the velocity is for the entire graph. So what should the velocity time graph look like? I have a positive constant velocity for the first 2 seconds, or sorry, a negative constant velocity for the first 2 seconds. And then I have a positive velocity, also constant, for the next second. So this is what my velocity time graph would look like, okay? Again, this still is constant velocity, but did the velocity stay the same the whole time? No, right? It changed. It was positive, now it's negative, or it was negative, now it's positive. This still counts as constant velocity because for any given time frame, the velocity is constant, okay? It's staying the same over some amount of time. Yeah?
So velocity doesn't just like increase gradually over time, right?
It could, but that wouldn't be constant velocity, it would be changing velocity. And I'll show an example of that in just a second. But in this case, no. If these lines are straight on the position time graph or a displacement time graph or a distance time graph, then that means my velocity or my speed is a straight line. It's constant the whole time. Didn't change. Yeah, it's fine.
But it's not possible to have the first graph like that, right?
It's not possible in real life, right?
We cannot go directly from this to this.
Right. You can't. This right here, this immediate change in direction, more importantly this, if you paid attention in algebra class, we call this a jump discontinuity, right? It would have a open circle on one end and a closed circle on the other end, and now you're writing a piecewise function. How much fun is this, right? That doesn't exist in the real life. This would be what we're going to call instantaneous acceleration. We're about to define acceleration. Acceleration is the change in velocity over time. Well, this velocity change didn't occur over time. It happened like that, and that does not exist. Not in the real world. So outside that door, you'll never be able to actually see it. It takes some amount of time for something to accelerate or slow down, accelerate negatively, right? So that doesn't really happen. But in here, I can draw a graph that it does. But actually, it probably took some amount of time. So yes, you are correct that this can exist, okay? Let's talk about acceleration. So the slope of a position time graph is velocity. The slope of a velocity time graph, let's think about that. So if I look at rise over run, the rise would be the change in velocity, v minus v naught. That's the change in velocity, final minus initial. V being final, v naught being initial. Right? So that's my rise because it's on the y-axis, rise, yay. Over, I'll write it out for a second, t minus t naught. But if I start at 0, then this would just be over time. Yeah.
So that's for what, acceleration?
Well, yes, this is the equation for acceleration. That happens to be what it is. This is the very first equation that's on your equation sheet. On the equation sheet, it doesn't look like this. On the equation sheet, they multiplied by t, and they added the v naught to the other side, and this is what's actually on your equation sheet. That's the second equation on the equation sheet, right there, second equation. It's the acceleration equation, but it came from this. So since rise over run is our slope, and it happens to be that that is the change in velocity over time, which is the definition of acceleration, that means our slope is acceleration. Question in the back.
Why would we do t minus t?
Because typically we just say that it's going to be t naught is 0. So since we can typically expect that, we don't really do it. It's technically change in time. It's technically final minus initial. So if you're doing some other section of the graph that doesn't start at 0, yes. But we don't really write it out ever, especially because this is the equation, right? You're going to use this equation to solve word problems soon. We just don't ever really write t minus t0 in. Like even if you're looking at a graph like this, and I ask you about some section of the graph, if I say from 2 to 3 seconds, you're not going to, if finding the thing, write 3 minus 2 very often. You're just going to say 1 second, right? So we just kind of blow that off, to be honest, is what happens. All right, so our velocity versus time graph, brand spanking new. Look at that. This one's constant velocity, so it's straight lines. Makes sense. Constant, stays the same. If its slope is acceleration, what's the slope of this line right here? 0, right? What's the slope of this line up here? 0. So when I have constant velocity, in this case, I have 0 acceleration, right? The slope is acceleration. And if I have constant velocity means that it's not changing. Acceleration is the change in velocity over time. So if velocity isn't changing, then there's no acceleration. Again, as me and Svarna discussed, yes, technically the velocity did change. So if I took the whole graph into consideration, there was some acceleration, but it happened instantaneously in a time of 0, which is magic, doesn't exist. So that's why we still call this 0 acceleration. Other questions about this? You could draw the acceleration time graph. Hey, why not add one more? We said there's a third one. Let's sketch it out. My acceleration time graph would just be 0. Right? We're going to talk more about acceleration after we do the pullback car lab and we see acceleration happening in front of our eyes. So I'm not going to focus too much on it today, aside from if constant velocity is occurring, acceleration is 0. Okay? Therefore, the acceleration time graph looks like this guy. Right? The way we got to that is that acceleration is defined as a change in velocity over time. Well, change in velocity over time would be the slope of this graph. That's how we got there. Okay? All right, we're going to do one example where we see what we can figure out from all this information, and then we'll do practice, and we'll move on. All right. I'm going to erase pretty much all of this. Let's go back to my very pretty cheetah that you saw me draw. That was gorgeous, and you thought, wow, that's a really pretty cheetah. Not, that looks like a weird newt. It's not what you thought in your head. You thought, pretty cheetah. So my example, my cheetah, her name's Cheetah. We've said this multiple times, but let's confirm. My cheetah runs 300 meters. We're going to define it. She actually ran south, 300 meters south in 3 seconds. She runs 300 meters south in 3 seconds. Before we start with the graphs, go ahead and make sure you know what her average velocity is. Calculate it real quick. And, not velocity. That's not an eraser, but it was close by. An average speed. Just double check. Should have negative 100. Because she was going south. and positive 100. Now, on our first day, we said we don't know what that cheetah's run looks like. She's going after the gazelle. She's at rest at the beginning. I know that. She's crouched over, looking at the gazelle, making eye contact, and then pouncing, right? But we don't know what the actual velocity looks like, so we can't say that much more about it. So let's suppose there are 3 possible options, okay? Option number 1, so I'm going to call this number 1. This is going to be her position time graph. For option number 1, it looks like that. So she just ran. What can you say about this? She just ran. Did she change speed at any time? No. She ran at the same speed the whole entire time. So if I took the slope of that line, what should I probably get? She runs the same speed the whole time. I know what her average speed must be. So if she ran at the same speed the whole time, what should this slope be? The average speed. Well, the average velocity, but yes, the average. If she did the same speed the whole time, the same velocity the whole time, then this has to be equal to her average, right? That makes sense. It's the only thing that does, okay? So that's what that looks like. That could be option 1. Option 2, option 2 actually is a little different. She did not do that. Instead, she stayed still for a bit and then went. That's option 2. So after she actually starts moving in trial 2, or in option 2, is she going faster or slower than in option 1? Faster. She has to be going faster. She wasted some time. She was still crouched on the ground. She did those 300 meters, not really in 3 seconds, but in like 2 seconds. She's wicked fast, okay? She did keep a constant velocity for the entire time after she started, right? But this has to be faster. When I look just at the line, what about these graphs tells me that this is a faster speed than this one here? What particular characteristic of the graph tells me that this one is faster than this one? Yeah?
The second graph is
Steeper, right? A steeper slope means it was going faster, right? Here's the tricky question. In which case, after she starts moving, in which case does she have a higher velocity? Option 1 or option 2? Which one does she have a higher velocity? Not which one is she going fastest, which one is she going to have a higher velocity?
After she moves, 1.
After she moves.
2.
2.
Okay, we've got votes for 1 and 2, so let's think about this. Remember, and this is the hardest part, a big positive is bigger than a little positive is bigger than a 0, bigger than a little negative, bigger than a bigger negative. So we know this one, she's moving at negative 100. I don't know exactly, but she's got to be moving faster.
150.
Maybe. I haven't told you how long she wasn't moving, so you can't calculate it 100%. But she has to be moving faster, right? So her magnitude of her velocity is going to be bigger. That's for sure true. So now looking at the numbers, which one has a higher velocity after she starts moving? 1 or 2? 1. Ugh, those negatives, they make life hard. Okay? So her magnitude, therefore her speed, is faster after she starts moving in 2. But her velocity is higher in 1. Any questions on that? Any questions on what that looks like? Okay, what is her average velocity in 2? What's her average? She was going still for a while, and then she's going fast. I don't know exactly when it changed. What's her average velocity?
it's still negative 100.
It absolutely is. Write this down. This is important. Okay, and this is where a lot of students get really flustered. Okay? Let's say, in order to do this, this time has to be 1.5. Then that actually is her speed for the last 1.5 seconds. The math will work. Okay? The first thing students will do when they're given a graph like this and asked for average velocity or speed, they will get into the average in their head. Since this happens at exactly 1.5 seconds, it would work out that 0 plus negative 200 divided by 2 will work, but that's very rare. If I had made this 1 second, and I had made this, that means I have to do 150. Well, if I do 0 plus negative 150 over 2, oh, no, that's not correct. So just taking the average of whatever two velocities are there, no. So then you're like, okay, oh my gosh, all right, okay. Now I have to like weight it. So do I multiply the speed by like 1 second and then I multiply the other speed by 2, and then you're really lost and confused. You're like, wow, an average velocity problem just became the end of my test. No. What is the definition of average velocity? Displacement over time. It is not the average of some velocities. That's not how we find it. We find it with displacement over time. So this graph would have said this is at 300, this is at 3 seconds, and you still would have used this equation. Write that down, make that clear, because I guarantee that's something that you'll mess up on my first test. You'll get a picture of a graph and you'll be like, aha, yes, I can average all the velocities because I know how long it was doing each. And then you're like, crap, what? I don't know what to do. Average velocity, even though we have a graph now, has not changed. It is displacement over time. That is it. Instantaneous velocity, I can't find without a graph. And if I have constant velocity somewhere, constant slope, then I can find it. Yay. But for average velocity and average speed, it's still displacement over time. There's a third option. We're not talking about acceleration in earnest today, but I want to show you what most likely my cheetah actually did. My cheetah probably didn't stay at the same speed because that would have meant instantaneous acceleration at 0 seconds, which isn't possible. Same thing, she's not going to waste her time. She's trying to catch that gazelle. It's her dinner. I don't feed her. I don't feed my cheetah. She's a hunter. I'm not going to feed her and then she not hunt very well. Like, that would be terrible. I'll let my cheetah roam in the wild, somewhere wherever cheetahs actually live. That's where my cheetah is. I keep her there for safety. Most likely, my cheetah sped up as she went. That's what most likely happened. She sped up. Okay? How can I tell based on this graph that she's speeding up? Somebody raised their hand. Yeah.
Because at the beginning we can see like the position going off slower with more time.
Right. This position is flat. This slope is flatter, so it's taking longer for them to move. Then the position is changing faster with less time. Faster with less time. It's speeding up. So another way to write that is it's going from flat to steep. Speeding up would be flat slope. It's taking a long time to cover a little distance. To steep, it's taking a very short amount of time to cover a lot of distance. So this, my cheetah is speeding up. What direction is her velocity still? Negative. Even though it's curving, it's still negative. I'm still going down. So that means I still have a negative slope the whole time. Even though it's changing, I still have a negative slope. All right, last thing I want you to do in this set of notes, I'll put the answers up in a second. I'm going to give you about 2 to 3 minutes to think this over. For cheetah scenario 1, 2, and I didn't put it on here, Trey, I want to see the velocity time graphs and the acceleration time graphs. I want to see the velocity time graphs and the acceleration time graphs for my 3 possible cheetahs. Cheetah 1, cheetah 2, cheetah 3. What would they look like? Get these to work really good. So you're thinking, what would the acceleration and velocity time graphs be to match my cheetah here? My cheetah's motion. Her 3 possible motions. Technically, she could have infinite motions. I don't know what my cheetah gets up to. I've never met her. She's in the jungle. They do have cheetahs at Fossil Rim in Glen Rose, which is only about an hour away. If you've ever been like, I want to see a cheetah, Miss Lemmer keeps talking about a cheetah. She drew a really poor picture of a cheetah. I need to see a cheetah. You can drive your own car in. So you drive your own vehicle. There is a very mean ostrich at the front. I'm terrified of ostriches. Terrified. And the ostrich accosts you. So all my windows are rolled up if I drive in. I've only done that twice in my life. And the second time, my parents made us do the safari where there was no windows. So the ostrich could have just gotten in and pecked my face out. Not cool with that. That and monkeys. Ostriches and monkeys. I've seen some monkeys steal some stuff in Thailand. All right, here are the correct answers. Let's see. Raise your hand and tell me, what should my velocity look like if my slope is constant and negative? Yes, constant, and is it a negative or positive? Or 0? Negative, constant and negative. If my slope's constant and negative, then my velocity will be constant and negative. Just like that. The slope of my velocity graph for scenario number 1 is 0, right? That's a 0 slope. So my acceleration is 0, right? For scenario number 2, what is my velocity for this first 1 second? 0. So I'm going to start at 0. And then I have a constant negative velocity. It's going to be like less than scenario number 1. But if your sketch doesn't show that, that's fine. And the acceleration the whole time is going to be 0. Now you might say to yourself, but hey, Miss Limer, it changed velocities. It was 0 and then it was negative, so obviously some acceleration occurred. Yes, but again, it didn't take any time. This isn't real world. It can't happen outside this classroom, but it didn't take any time. So no chunk of time on this time graph should show acceleration because it happened instantaneously. Last one's tricky. Let's see if we got it. So this is increasing slope. So it's getting faster, 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 faster. But that means my velocity, since it's negative, is decreasing. So I would have a decreasing negative velocity. That shows speeding up. If you're starting to read velocity time graphs when we get into constant acceleration, this means speeding up. The way I can tell it's speeding up on a velocity time graph, it's not the slope, right? It's how far I am away from the x-axis. The faster I go, the further I am from the x-axis, either above or below. But that's how I can tell, yeah.
So with that graph, would that mean that the velocity is increasing at a constant rate?
Most likely, yes. And let me clarify that statement. In AP Physics 1, any of the questions you're going to do that involve calculation, that's definitely going to cause this to be a constant slope. Any of the times you're finding a graph from a position graph, you can expect it to be constant slope. The reality is our brains can't see the difference between that being a quadratic function or a cubic function, which this one's quadratic. So you just make the assumption it's quadratic. Okay, so let me show you something. If I finish this out, this acceleration, I have a negative constant slope, so I would have negative constant acceleration. So something you will notice, and something that goes back to the calculus of it all that I can't teach you, is a pattern. Okay? When I look at all 3 graphs, there is a pattern. If my first graph, going up from position, velocity to acceleration, if my first graph, and this is what our constant velocity is today, if my first graph is linear, everybody see the linear of it all? My next graph will be constant, and my next graph will be 0. That's a pattern that will always hold true. If my first position graph is linear, then I'll get a constant, then I'll get a 0. If my first graph is curved, my next graph will be linear. My next graph will be constant. There's no graph past that, so I don't care. But that's the pattern. It goes curved to linear to constant, or linear to constant to 0. That's the two possible outcomes. So his question, could this be greater than curved? No. If this is curved, then we expect it to be linear and then constant. That's what we expect. Come to AP Physics C and I can change that. Can't do that here. Okay, I'm done.